Alright, hello everybody, my name is Jeremy Allred, and this video is going to be about the Zeeman effect. So I'm going to start off by going over a few simple topics that will hopefully clarify a little bit of what I'm going to talk about later on. Hopefully they won't be too redundant or mundane to start off with, but I just think it'll be useful as we start to learn a little bit about the Zeeman effect. So I'm going to first go over the electromagnetic spectrum, and then talk about what the quantization of energy is. So this is the electromagnetic spectra. It's pretty basic. Hopefully you already know a little bit about what this is, but basically it includes everything from gamma rays to radio waves and also visible light. It's just a combination of what creates electricity and magnetic fields, and I'm not going to go into too much detail about this, but we know that it expresses a wave-particle duality, and we know about Maxwell. We've talked a little bit about him in class, and his equation, c, the speed of light, equals frequency lambda, or wavelength. So that's just a little bit of basic background of this, and the electromagnetic spectrum is just all wavelengths of electromagnetic radiation, and technically it's pretty infinite on both ends. So the quantization of energy. This is something that we've heard about a lot. You probably heard quantization many times, especially in physics class. We talked about it pretty extensively. But basically, classical energy is what we usually think of when we think of energy. And it can exist in any real value. But quantized energy, or quantum energy, just means that energy is divided into certain levels, and it jumps from one level to the next. Like you can kind of see here, this red line is a classical model, and these kind of stepped blue line is a quantized model. So I think that the easiest way to think of this is kind of like stairs, going up a hill or going upstairs. On a hill, that would be classical energy. You can be at any height along that whole hill, like this line. But on stairs, you can only be at certain measurable heights. And you can't be in the middle, you can't be halfway up a stair, you have to be on the actual stair. And that is how energy is quantized into these different energy levels. And kind of the place that we see this is in atoms on an atomic level. So I'm going to show you this little thing. This is like a little photon or an electromagnetic radiation coming at this atom. And we know is when it comes, this electron right here will be excited and jump to a higher energy level. And this can happen in reverse as well. This electron will jump from a higher energy to a lower energy and release a photon, release electromagnetic radiation. And what we know is that these different energy levels through which the electron can move from one to the next are quantized levels of energy, or they come in steps. It is not just any energy. They are very divided and split into specific different energy levels. And because of this, we see something called an atomic spectra for different atoms. We see emission spectrum and absorption spectrums as well. This right here is just a continuous spectrum. It's all the light. But with different atoms, when they emit different levels of energy, when the electrons jump from a higher energy to a lower energy, they will emit certain wavelengths of light. Only certain specific ones that are quantized along this spectrum. When they absorb it, on the other hand, they will absorb only the certain levels, because for an electron to jump to each level, they have to absorb that exact particular wavelength to be able to make that jump. And each different atom, each different element will display a different emission and absorption spectrum. So we can identify different atoms by this spectra. And now we're going to get into what the Zeeman effect actually is. These right here are spectral lines that I was just talking about. And that is what Peter Zeeman, who is right here, studied. He was a physics student, and he studied it with his mentor, Hendrik Lorentz. And they eventually won the Nobel Prize for their studies in physics in 1902. What they observed in their experiments was basically a splitting of spectral lines that occurred when they were acted on by an external magnetic field. It's pretty complicated, this splitting, but in basic terms, the separation of the lines is proportional to the size of the applied magnetic field. So basically, like right here, this is no magnetic field. You just have the single spectral line. When you have a small magnetic field, they split a little bit, and then when you have a large one, they split even more. So somehow these magnetic fields were interacting with the spectra to quantize energy in different ways and split that quantization, that energy level that is already quantized, into more quantized energy levels. And Peter Zeeman kind of figured out why, so we're going to talk about that. Right here we just have kind of a basic model of an atom with the electron going around in its orbital, and we're going to look at the reasons for this splitting. So we know that electrons are negatively charged particles, and they move around the atom like this in their orbital, and as they move around, they create a current. And this current, this moving current, will create somewhat of a magnetic field around the atom itself. And what we know is that this magnetic field, when it is applied, when there's an external magnetic field applied to this atom, the magnetic field of the atom will interact with the external magnetic field. And what happens is these two magnetic fields try to align. As they try to align, work is put into the system and energy is put into the system, and that splits the levels of quantization and thus splits the spectral lines that we see. And what is interesting is that when we apply this magnetic field to this atom, and it kind of tries to move it and align it like we're seeing here, there are only certain angles at which we see this splitting. So what we learn from this is that not only is the magnitude of these electron orbitals quantized, or the energy levels, the amount of energy, but also the area in which they exist. So there are only certain angles at which the atomic magnetic field and an external magnetic field can interact, like we see here, and that we call that space quantization. So those are two different levels of quantization that occur, and this space quantization is why we see the splitting at quantized levels. So going back to kind of those lines we looked at how they'd split, they were split into very specific and different lines, and that is because of this space quantization. Now, one more thing that Zeeman noticed as they started to study a little deeper is that there is a very small amount of splitting even when there is no applied magnetic field. And this splitting can only be seen with very precise instruments. It's known as fine structure. And the fine structure is just splitting that line into a doublet. So every single line you can see here on these spectrums, on these atomic spectrums, is a doublet. Even though you can't really tell unless you have very fine instruments, it is split into a doublet. So why does this doublet happen? We already talked about how an electron going around an atom creates a magnetic field. But what we kind of have learned from fine structure, from this doublet, this tiny splitting, is that electrons themselves have a spin. They spin in one of two directions, and we say it in a few different ways. It can either be plus 1/2 and minus 1/2, or we often refer to it as an upspin or a downspin, like it says right here. So, like we already mentioned, since electrons are charged particles, as they spin, they create a current, and they create their own little magnetic field. This spin, this intrinsic spin as it's called, creates an intrinsic magnetic field. And this magnetic field of the electron will interact with the magnetic field of the entire atom, causing the doublet. And it's a doublet because the electron can only have an upspin or a downspin, so only two different distinct lines. So that's what we've learned from the doublets. Now, just to kind of review a little bit, that's the basic idea of what the Zeeman effect is and what it kind of taught us about the different levels of quantization. So what we know, what we've learned, is that each atom has electrons spinning around in an orbital, and that creates a magnetic field. And also that each electron is spinning around itself, either up or down spin, which also creates a magnetic field. And these two magnetic fields will interact with each other and give us this doublet of splitting, like you can see right here. starts out as just one, or it looks like it's just one, but when we look closer, it's really a doublet because that electron will spin up or down, which splits this into two different quantized levels of energy. Now when we add a magnetic field to this and we apply it, it will create even more splitting because of space quantization like we learned. So this top one is with zero, with no external magnetic field. The middle one is with a small magnetic field, and this bottom one is with a larger magnetic field, so larger splitting. And that is just because only certain angles of interaction occur, and those certain angles will cause certain levels of quantization. So we know that energy is quantized by magnitude, by the space it's in. There's also that intrinsic field, an intrinsic spin of the electron, which creates these doublets. So that is what is known as the Zeeman effect in its basics. And one application, at least, that I thought was very interesting and relevant is magnetic resonance imaging. This is an MRI machine, and the way it works is by focusing on the interaction between intrinsic magnetic fields of a hydrogen atom and biological molecules in the body. And we use this to create images. I believe that it's the H2O molecules in the body, when you are able to align them in certain ways, and because of their intrinsic spin, we're able to image them with this machine. So that has been a very profound application of the Zeeman effect and of this intrinsic magnetic field of hydrogen. So that is all that I wanted to talk about with the Zeeman effect. Thank you very much.